All right, last week of lecture. If Tony and here, if you could quickly spin your homework. Last week of lecture. So at least in my class, I don't know about everybody else's class, but so you guys have made quite a bit of progress. We are just gotten through instruction level parallelism. We discussed in previous lecture this example of a 4-stage adder, where you have feedback and you're making a decision, and you're taking advantage of instruction level parallelism to be able to do a cumulative sum of 20 integers. In this case, it took 30 cycles, but if you were just doing it one and then feeding it back, if doing it like a single cycle instead of and it would take you 20 times 4, which is 80 cycles. So your improvement in performance, your speed up is 8/3. Now we're going to get into this concept of thread level parallelism. So what we're doing before is using the same architecture to do multiple instructions. So now what we're doing is, when you do the same thing, quickly turn your homework in, using multiple processors to be able to either do the same instruction set or do multiple instructions simultaneously. And there's 3 types of ways of doing this. We're going to talk about coarse grain and fine grain multithreading, and we're going to talk about this concept of SMP, which is simultaneous multithreading simultaneous multithreaded processors, or simultaneous multithreading. So the whole idea behind multithreading is performing multiple threads of execution in parallel. They're happening at the same time in the same computer on different processors. So you're going to be replicating registers, program counter, data memory, instruction memory, whole 9 yards, controller. It's all going to be controlled by the operating system. And we have to have this concept of fast switching between threads. And what we mean by that is we don't want to leave one of our processors idle for too long. So if we have 4 processors running and we have a lot of deadlock, meaning that we have one processor waiting on another processor's result, we want to be able to use the operating system, be able to reallocate that processor to a different set of instructions. So what you would do is you would take your instruction memory, since you're not familiar with this, you would actually write everything from your instruction memory to your file output, put that in a page in your non-volatile memory, bring in a different set of instructions using the operating system, load that into instruction memory, and then run a whole different set of instructions, and it will stop once the operating system says, no, we need to reallocate that to the previous instruction. So it actually store the instructions and the program counter of the last instruction that you executed. And so we have differences here between fine-grained multithreading and coarse-grained multithreading. So fine-grained multithreading, you're switching threads after each cycle. Every cycle, you go to a different thread. You interleave the instruction execution. So once you do a different cycle, you're doing a different thread with the processor. And if one thread stalls, you then go to another execution. So if we have stalls, and we're talking about if we have instruction level parallelism, what's our main type of stall? If we have both data forwarding and execution hazards, what's the one time we have to insert a stall in pipelining?
When the result isn't ready to be used.
Okay, well that's when you have to insert a stall. But what's the one scenario? Because before you'd have to wait for everything to go from ALU to data memory to write back, and we find out we can forward it to the ALU in the previous stage. But there's one instance where we have to wait when we have to insert a stall. Load word. Very good. That's what I'm looking for. So if you have a load word situation in a fine grain, you just, while that's happening, you would put in another thread, put in another execution, execute another instruction in that thread, and then come back, so you actually wouldn't lose any performance.
Wouldn't like all this switching, it would cause a lot of heat, but wouldn't it be
cost
a lot of time to switch?
And that is a big operating systems problem. So it's a little outside the scope of this particular course, but yeah, it's the operating system has had to make a lot of decisions about threading, which is why sometimes they do other things called coarse-grained multithreading. So you only switch on long stalls. So here I describe a level 2 cache miss. You miss in the cache, you go to the next level. You miss in data memory, it's not in the cache. You go to level 2 cache. Well, if you're doing all this time, if you recall, you're going to be waiting a while. You might as well just put in another thread and execute that. So it simplifies the hardware, which kind of goes into what you're talking about, but it doesn't hide short stalls. So we were talking about load word, it doesn't hide those very well. So in order to kind of combine both of these approaches, we're going to do something called simultaneous multi-threading. So in simultaneous multi-threading, we call it multiple issue, meaning that we're going to be issuing multiple instructions simultaneously. If you're able to execute multiple threads, you do it. So you schedule instructions for multiple threads, and the instructions from independent threads execute when the function units are available. And this diagram that I'm going to show you down here is going to describe basically what that means. So here we say there might be 3 or 4 threads available, and we have, in a particular, we need 2 issue slots here for A and 3 for B, right? So if we had 4 available to execute, we do the SMP. We would do these first and then these 2 simultaneously. So within threads, dependencies handled by scheduling and register renaming. So we're going to be going over something called Tomasulo's algorithm when we talk about register renaming. And the general idea is that if you're doing a loop, and remember how in your project description I had you go through each execution of the loop to figure out precisely what's happening? The reason why I had you do that is not just because it's good project planning, but because it's a good way of understanding how multi-threading works. In order to do loop unrolling, which is what you did, if you want to execute both loops simultaneously to speed up the process, you would actually rename the register in the second one. So you'd use S0, S1, and S2 in this one. And then what you would do is you just know that there's going to be some sort of calculation. So you would use S3 and S4 and S5, and then combine them together to be able to properly get the right result. So this diagram is a really good description of how coarse grain, fine grain, and SMP work. So I'm going to, actually, yes, I can fit the whole thing here on one screen. All right, so you have 4 threads of execution, and we have 4 potential issue slots to be able to do that. So we can execute 4 instructions simultaneously in this processor. So in coarse grain, here's what it means. So every cycle you go through. So coarse grain was the second one I defined. So you would execute everything until a stall, right? You switch on a stall. So here you're executing this portion first. And then once you get a stall, then you go here, and you see how that matches down there? So you get a stall, and then you go to the next thread. So if you were to get this stall, you would go to thread C, and you would get this stall, and then do thread D, and then after this stall, you would go back to thread A in coarse grain multi-threading. So that deals with less switching, which goes back to Joseph's question. It requires less hardware overhead, but you can see the performance is not as efficient. If we go to fine grain multi-threading, we do this every cycle. So the first cycle is this, right? Second cycle is thread B. Third cycle is thread C. Fourth cycle is thread D, as you can see. And then the fifth cycle goes back here. Then this one is next, and so on, right? So that's the difference between coarse grain and fine grain multi-threading. Fine grain multi-threading, you switch threads every cycle. In coarse grain multi-threading, you switch threads every stall. Now, simultaneous multi-threading, since we have 4 resources, we should try to use 4 these. So we start at thread A and thread B. And you see how thread A here is the first 4, and thread B is the next 4. So the next cycle, we have this one and these 3. And you can see how it's this one and these 3. And then the next one is this one, and these 2. So you can see that's there, there, and there, right? See how that works? We're trying to use them simultaneously in order to be able to try to use the resources you have as efficiently as possible. And you can see they kind of overlap and overlap. Now, here's a question. This one down here is white, right? Well, here's what's happened. We get down to this point, and we have this one here, and we use these two, and we're waiting on stalls and stalls, right? So we have these two here, this one here, and then we would look at thread A again, and what do we got? Nothing. Okay, that should be here. I should make that circle here, right? And so the next one we execute are just these three. What are these next four?
So you would not just put whatever the next thread's available.
Correct. Because A and B are both stalled.
But would you start at the beginning of the next thread B?
In this case, they didn't. They're actually going to go through like so. This is the algorithm. You could design it that way, but to get back to your previous question, it requires a little more hardware overhead. So again, good design requires good compromise. So does this make everything we talked about earlier about coarse grain, what multi-threading is, coarse grain multi-threading, fine grain multi-threading, and simultaneous multi-threading? Yes, Brian.
So if I'm understanding correctly, if we go back to the instruction parallelism, when previously we would have had stalls, we're just starting a different instruction? Is that what's happening? Okay.
Yes, exactly right. So we had a situation where we had a load word, and we were loading it into S1, and we had add, and one of the ones is over here at S1 here. And let's say we had another thread of where we would have add S3, S4, and S5, right? So let's say we execute this and we realize, we have to insert a stall. Well, what the operating system says is, I have to wait one cycle for this one before I get the data that's forwarded, so I might as well do this guy. That's what's going on. Any other questions?
So which one would, I guess the SMT, that would be the highest performance?
Yes. Because you can see, if you look at it from the perspective of, are you executing thread A, it's fast, not really, because here, it's executing here. But you're getting all four threads through, and that gets back into overall system performance. So if you're trying to do an Allen's law comparison, then yes, it is. Any other questions? All right. So, in order to run all of this, and this is probably something that popped in your head by this point, we're going to talk about centralized versus distributed memory. So this will be another big definition. You want to just define and differentiate between centralized and distributed memory, give the pros and cons of each, and then typically students will do a little drawing to be able to differentiate. Oh, I'm sorry. You can either do the definition or do the drawing. Both say the same thing. I'm going to explain why they're the same. So centralized memory. So all the memory is in a shared memory multiprocessor, which is down here, right? And everything is done over a large interconnection network bus. And so you have to communicate everything back and forth between your shared memory, which talks to multiple processors. And so what's going to happen is that for each processor has its own cache. And so you can satisfy memory demands with a small number of processors just by doing proper cache allocation in centralized memory. So the definition here, the pro, large caches, single memory can satisfy memory demands of a small number of processors. However, as you add more and more, right? If you add more processors, so if we have an 8-core processor, or you try to go 16 or 32 or 64, right? The more and more, it becomes more and more difficult to be able to distribute it properly using this cache coherence concept, right? And so scaling it to a large level becomes difficult. So here, if you do this drawing, how do I want to have you guys convey it? No, you know what? Don't do the drawing. Just for the exam, do define centralized and distributed, and give me the pro and con of each. Because one thing that doesn't say, the drawing doesn't say, is it doesn't describe scaling beyond what's technically conceivable part. Yes?
So for the TGO, we don't have to do the drawing?
Yeah, for the TGO and here. Here, I'll just end there.
Okay.
I'll make it that way. Is this on my Word document? I probably don't even need to. There. Is that clearer? Let me do the same thing for 8.8. All right. So when we talk about distributed memory, the whole idea in this drawing is each processor has its own data memory. So each processor has its own copy of local memory and its own cache within each processor. And so being able to distribute that as you get more and more processors in a multiprocessor becomes cost effective. It reduces your memory bandwidth requirements. And the one problem, though, is trying to communicate data, right? So let's say I have a copy of X here in this memory, in this cache here. I have a copy of X in this cache here. Actually, we're going to talk about that in cache coherence problem next. What happens when I update one, but I don't have the other value yet? So here, physically distributed memory is a cost-effective way to scale memory bandwidth if most accesses are to local memory. So then you're able to do this if you're taking, what's the word what am I taking advantage of here? What design principle of accesses to local memory?
Okay.
Locality, yes. There's the keys are in the details. Local memory, locality. So basically, once you have locality, and you design it in such a way, you can take advantage of that to improve performance through multiprocessing. And therefore, that reduces the latency of local memory accesses. However, if for whatever reason your operating system is trying to use multiple processors to do the same instruction, then communicating data between processors becomes more complex. And we'll talk about that in this cache coherence problem. And if you recall at the beginning of the section, I talked about why multi-processing was such a problem is because when you tried compiling it down to the architecture level, it became this issue of not being able to properly distribute the code in order to be able to do it efficiently. So we have to deal with the proper software design in order to take advantage of this increased memory bandwidth. So when you did your introductory classes in Java, all of this stuff is ignored, right? Because they just compile it down for you. But when you're dealing with the architecture level, especially if you're going to be electrical engineers in the field, you have to understand what's going on in the underlying architecture and how your code that you're writing impacts it. Which is why in your final project, I'm having you go down to the assembly level and then to the machine level. So you demonstrate a thorough understanding of the whole computer system. If you can do that, you've demonstrated that you thoroughly understand how a computer works. It may not be the exact same programming language. It may not be the exact same assembly language. It could be ARM. It could be all kinds of different things. And for a different architecture, it'll be a different machine language, but it'll be the same. It's all ultimately the same concept. So, dealing with this cache coherence problem. So here's what I was about to draw out. In this case, what we see here is we have 3 processors, and each of them has the value of u, right? And so this is a centralized memory processor where processor 1, processor 2, and processor 3, we have an instance where they were all initially 4. Then what happens is processor 3 updates it to 5. Then it goes to the centralized memory. It updates 4 to 5. It updates to 5 here. But while it's updating, it updates it again to 7. So this would be an instance where you have I++, and it does another quick loop. So processors are going to see different values. So let's say my next instruction occurs in processor 2, where I have the value of 5. Or what even worst case scenario, I have an instance where it's in the process of updating here, processing. So here it was 4 and it's changed to 5. This value is changed to 5, and I need the next instruction here. So now, how do we do multi-threading? We have to insert stalls in order to maintain this concept of cache coherence, meaning that each cache is going to have a copy of the variable in order to perform it, but the values are incoherent. They're not the same. So how do we deal with this? And we're going to learn about 2 things here called directory protocols and Snoopy buses. So cache coherence defines the values returned by a read, and cache consistency is what happens when we write to these different values, right? So dictionary-based coherence and snooping. So the whole idea with dictionary protocol is that you're using existent hardware in the processor to maintain cache by using bits as like some concept of a dirty bit. And what you're doing is kind of like the same thing you were doing with in section 5 when we were talking about set associativity and direct associativity, where you use the valid bit to determine whether or not it's been written to in order to improve memory access time. So we're using existing cache hardware like an invalid bit or a dirty bit to maintain cache consistency. So what we're doing is we write to a value of the cache, and what's going to happen is if we've updated it, this invalid bit is going to look at the other 2, and they're going to see that they're not the same, and then the processor is going to automatically update it. This approach allows the state of cache coherence consistency to be more distributed, but introduces higher delay, as CPUs must request that a bus like the Snoopy bus has not yet updated. So the whole idea of the Snoopy bus is you have, let's say we have 3 processors here, and Brian has updated value u, and I'm the Snoopy bus. I'm going to be constantly checking to see what they're doing, right? So I see Brian's updated his copy, and so then what happens is the Snoopy bus protocol is going to say, I need to allocate the interconnected bus, and I need to tell Xavier, okay, the value of u has been updated, and I need to tell Clint the value of u has been updated. But that has some sort of delay, but that improves cache coherence. Cache consistency. So we define snooping as a Snoopy bus protocol that can help ensure consistency across caches. It works by monitoring, aka snooping, the different caches and overseeing what operations the processors perform on the data. Kind of like how I just described here. So this description I put here of write through and validate is what I just described. Basically, the Snoopy protocol is using these dictionary-based coherence. I'm saying when Brian's processor updates his copy of the cache, he's going to say, all right, his invalid bit is different than Clint's and Xavier's. So then I say, hey, we need to fix this one, we need to fix this one. And having this approach becomes distributed when you have 6, let's say there's 28 of you, so let's say we could theoretically have a 32 processor. So let's say we have a situation where I have to manage the bus for all of you, and Brian has his copy updated, and NOV is the only other processor using it. So I have to say, all right, I need to allocate the bus, I need to take it over here, I need to tell NOV that this value's been updated, I fix it, that I'm constantly snooping, does anybody else need it? Then for some reason, Paranthe's processor suddenly needs the variable, then I need to check both of them, right? So this is where bringing locality into play becomes very important, is you start having massively parallel programs. For example, in video games, especially online distributed video games, where you have to be able to render all this information while simultaneously calculating. Like you have a character in World of Warcraft, and I'm going to admit my ignorance in World of Warcraft games, but there's some sort of potions and weapons and that all have different values, right? So if we're all in a World of Warcraft siege, please tell me that's right, and we're attacking something, it's a giant, dragon. Here's our dragon we're attacking, right? So, which looks like Batman, but whatever. Okay, so we're attacking Batman in World of Warcraft for some reason. And so we all have different levels of weapons, potions, spells, whatever it is, right? And every time we get hit by the main boss, we lose some value, right? Or we could gain value by finding a maiden and she sells you a potion or however it works, right? A lady in the pond throws you a sword and you become the king of England. So all of that has to be kept and maintained, right? So we have 64 of us all playing, that becomes the thing. And if you're the processor at people at World of Warcraft and you have millions of people who are addicted to this game all over the world, all playing their different maps, you have to maintain serious processing power in order to do this. So it requires some serious simultaneous multi-threading. And if you have a battle, you're going to have a lot of people talking about, is there anything shared? Do people share things in World of Warcraft? No idea. Okay, let's assume that things are shared. We have a jar. Me and Shakira, we have a jar and we're fighting World of Warcraft Batman ghosts. And that's something that we need to share, right? Well, we have a shared variable in their system. So if for some reason she needs it, we need to both know that that value is reduced. And so that means, the first thing is on the processor maintaining Shakira's, I say, I'm going to take this, I'm going to update the value, and then if I'm expecting 10 units of stuff, and there are only 3, but I need 5 in order to continue the fight, well, I might think, what if I go in thinking I have 5 and suddenly I have 3 and then I get killed, right? So in order to be able to do that, you have to make sure that you have massively parallel processing. And all of that is using this write through and validate. So I played a lot of Mario, but that's not much multi-processing and going this way for years. So does this make sense to everybody? Does anybody have any questions about cache coherence, cache consistency, write through and validate, snooping, dictionary-based coherence? So basically this question is describe how dictionary-based coherence and snooping are used to maintain cache consistency in a multiprocessor. So at this point, we're going to start talking about this concept of Tomasulo's algorithm. So this actually was developed in 1963 by Robert Tomasulo. And this before that, it was people had to it was essentially multiprocessing had not been done. And so I actually mentioned here that it received it's a very prestigious, the Eckert-Maltby Award in 1997. Basically, you have to do some sort of fundamental development of in computer engineering and computer science. Nowadays, it's slightly behind the Turing Award in terms of prestige. The Turing Award, you can think of it as the equivalent of the Nobel Prize in computer science and engineering. And so basically, you have all these different execution units. So you're talking about floating point units. You have integer execution units. a common data bus, like that's what we were just talking about. We have this interconnection bus between multiple processors. What we're going to have is we're going to have these instruction units, and we're going to have something called reservation stations, where we're going to be holding data until we actually start dealing with actual, we start executing it. And everything has to go through this common data bus on which computed values are broadcast to all the reservation stations that may need them. And the whole goal of Tomasulo's algorithm is to do this concept of out-of-order execution. Up to this point in everything you've done in code, in all your projects, you started here, you did this, you called a function, you did a function, you came back, and you got to the end. Sometimes, and Tomasulo's algorithm will calculate when it's possible, you can execute the instructions out of order, which will give you improved performance, but will give you the exact same result. And so the whole goal is to improve high performance without special compilers. Up to this point, we've talked a lot about compiler-driven encoding of the microengine. One of the challenges of a compiler-driven encoding of the microengine is you expect the compiler to go specifically to that microengine. And if you run code expecting that compiler on a different multi-threaded microengine, it suddenly becomes challenging, right? So being able to improve the performance through parallel processing without having to change the compiler becomes really important. So this in-order issue, out-of-order execution is this idea of dynamic scheduling. So the whole idea is I may have instructions 1, 2, 3, 4, and 5, right? But I may need to insert a stall between instructions 3 and 4 that may take a while. Or that instruction 3 might be a floating point division algorithm, and instruction 4 might be an adder that doesn't require that variable. Instructions 4 and 5 could be an adder that don't require that variable. And if you recall earlier, we talked about we had division, we had restoring and non-restoring division and required number of cycles, and multiplication requires a number of cycles. And while you're doing all these cycles, you have other instructions that aren't being done. And if you get those instructions done while you're waiting, you can actually significantly improve your performance. And so we're going to have these registers and instructions that are going to be replaced by values or pointers to reservation stations. And we'll be going over all these the ways that reservation stations are used. But we're going to have this concept of register renaming, which I've alluded to a couple of times. If you're doing a loop, and let's say instruction 3 in this loop here is a floating point multiplication instruction that requires 8 cycles. And 4 and 5 are further on in the loop and are not dependent on this result. And I do a second loop. So this would take me 16 cycles, and I have 4 and 5 twice that don't need to wait on me, right? So why not just get them done? But here's the thing, in order to do them out of order, in the second loop, I would rename the variable here the second time through in order to be able to execute it, so that way I can do them in parallel, get it done, and then when I'm done with my 2 floating point multiplications, we're through it and we can move on. And it's all done at the hardware level. It's no additional software. So you don't have to change the compiler, which means you can improve your multi-threading without having to deal too much with changing the code. So Tomasulo's algorithm, even though it's been improved a lot over the last 50 years, this is a fundamental discovery in how to get from your single cycle data path to a multi-threaded processor and significantly improve performance without having to deal too much with how they've already had the compiler driving the microengine. And so the two main advantages, distribution of hazard detection logic. So the whole goal is we need to make, let me scroll up a little bit for those in the back. Probably can't see these two advantages. So since they're more we're going to discuss why this is important in a second. We have more reservation stations than registers. Therefore, you can do optimizations that compilers cannot. Register renaming, being able to distribute values to complete faster processing. And the advantage there is distribution of hazard detection logic. So before we just had this, the pipeline data path, we had our hazard detection unit, right? And if we detected a hazard, then we would flush the instruction out by putting control signals of all zeros. So now it's distributed, which improves our ability to detect a hazard. And elimination of stalls for what are known as right after read and right after write hazards. So everything that you've had up to this point are what are known as read after write hazards, meaning that you want to update the value in the register, right? And then you need to read it the next instruction. So read after write. So everything in MIPS is designed to eliminate these right after read and right after write hazards by maintaining pipeline stages and having a flow. So, if you're trying to read it, and right after read would occur if you had instruction memory and data memory together, and you'd have to add all kinds of different hazards to eliminate that. And then writing after writing again, so you're doing a load word, store word, another store word, and you're creating, let's say your store word, you're taking your base pointer, right? No, here's the better way, wait. You're writing to the registers to update the base pointer, and then the next instruction you're trying to do a store word, and you haven't completed it yet, so you're actually accessing the base pointer in the wrong place. So the store word, that would be what's known as a right after write hazard. So here's the whole idea of Tomasulo organization. So you have all these instructions. In this case, it has 3 floating point adders, 2 multiplication, and you have floating point registers where you're going to store values, and your operations queue. And everything goes over this one common data bus. So let's say you have a result here and you're writing a result back to memory, right? And then you have another instruction that completes right around the same time. It has to wait until this instruction completes, and we'll just, in the next example, we're going to be going over that before it can pass it on to the floating point registers. So you're going to be maintaining copies of variables. You're going to be doing a lot of register renaming, and you're going to be using these floating point registers in order to store temporary copies. So I think these 3 stages of Tomasulo's algorithm, and then the next we're going to be going over this example. So there's 3 stages. Hopefully this will make the diagram I just showed you make more sense. First, you have to issue the instruction. Just like anything else, you have to get the instruction from instruction memory. Here you get the instruction from the floating op queue. So if we, excuse me a second here, we go back up to the drawing. Your floating op queue is where everything's stored here, right? So you get the instruction from your floating op queue, and if the reservation station is free, meaning we have no structural hazards, then we can just put the value and control issues the instruction there. So what that means is, let's say I have 2 load buffers, right? So I can two load instructions back to back. But if for some reason I have a 3rd load word instruction, I have to wait until one of those 2 reservation stations is allocated. Is done. It is no longer allocated. 2, you execute. Do what it needs to do, just like anything else. When both operands are ready, then execute the instruction. If not, you got to watch the common data bus for the result. What that means is, if you have your operands, let's say you're doing an R-type instruction, right? And you have 2 registers that you need, you have to wait for that second value to come back to the common data bus, update it, then you execute. And then 3, the write result, you want to finish the execution. You actually have to send the result over the common data bus to the place where you want to store the result. So, for example, if you're doing a load word instruction, you got to go to the data memory, get the information, allocate the common data bus to be able to write to the registers in order to be able to update the register. If it's an addition, you have to use the common data bus to update the register that you're running back from the integer or floating point arithmetic logic unit. So here, write result, finish execution, write on common data bus to all awaiting units, and reservation station if available.
Mark reservation station available, meaning that if you have 2 floating point units, both of them were being used, one of them is no longer being used because you've just finished the instruction, then you can load another adder instruction into that. So the whole goal is to be able to try to see what instructions can be used where by using these reservation stations, by doing what's known as in-order execution and in-order issue, meaning the instructions are issued in order just like before, but they're going to be executed out of order based on the availability of the reservation stations and the ability of them to calculate it in a proper order that maintains cache consistency. So every instruction you issue it, as clock cycle, you execute the instruction when the reservation station becomes available, and then you write the result over the common data bus, and then you tell the rest of the architecture that your reservation station that you were using is now available. The example question that we're going to go over here in a second should clarify any questions. Give everybody one more second here to write out. All right, so you're talking about register renaming and reservation stations. So here is our example question. Where's my view? All right, that's actually awfully small. All right, so here's the way a Tomasulo problem would be phrased on an exam. So the whole idea is that we're given 5 instructions. First one, and the reason if you're doing it in a multiprocessor, you have different names for it here based on that different type of instruction set, but the same concept. So load data, multiply data, store data, sub I, branch not equal. The same issue, except load word is a 32 bits, so here it's load data. So floating register F0, we have our base pointer to our original R, here we call it R1, right? And multiplication, we then take the result from F0, multiply it with F2, and store it in F4. And then we're going to store F4 into 0 of R1. So we're just updating a copy by multiplying this value by F2 and then storing it back. In the meantime, we have sub I, R1 8, this pound 8, that's just the same thing as 8. So you could actually, for the, no, I'm going to keep that because that's part of the, I left that specifically in there. I could have changed this to match the MIPS architecture register transfer language that you have in your grip screen sheet. But this would be, since this is in the grad textbook and you've already exceeded all of your textbook material, this is the instruction set from the graduate textbook. So just to get the idea that different architectures have different register transfer languages. And then branch not equal, we compare R1 and R0, and then we loop. So this part here is where Tomasulo's algorithm kind of becomes important in understanding the nuances, this part of the problem. Show the execution of a single issue Tomasulo algorithm. That means we're issuing them in order in the form of the status tables for 2 iterations of the above loop. So here's what's going to happen. Every loop, we can kind of translate this back up to C level, right? So basically we can call this A of 0 equals A of 0 times I, right? We'll just call that variable I, where I is F2, and this is the base pointer is R1. So we load it to F0, and then simultaneously we have the base, let's call this J. And here we go, J minus 8 every loop, and then we branch if J and K are, if J and K is not equal, right? So what we're doing here is we have in this problem we have one floating point add subtraction unit, and we have one floating point unit. And the reason why this is important is because if we had 2 floating point multiplication units, we could do 2 of them in parallel, right? And I have another version of this problem below here where I actually changed the problem up a bit so you can see the improvement in performance. 1 load buffer and 1 store buffer. So that means if for some reason we have to load this value first, we had another load word instruction, we could do 2 loads simultaneously if we have 2 load word buffers. So floating point add and subtraction takes 2 cycles, multiplication takes 4 cycles, divides takes 16 cycles, and stores take 3 cycles for execution. Additionally, the first load takes 8 clocks because we have an L1 cache miss. Second load takes 1 clock because it's a hit. So here we have described a situation in which we have requested a load word value that we need. It's not there. We have gone into our non-volatile memory. We have grabbed the page. We've brought the page back in. We now have the entire array that we need. So we now get load 1. First takes 8 cycles. That's every subsequent load will only take 1 cycle because we have the data we need. So this is a really good combining concept type question because you understand arithmetic, you understand memory access, you understand performance, you understand multiprocessing, you understand load word and store word, and you understand cache hits and cache misses. So this is a really good way to kind of summarize everything you've learned this semester into one big problem. Function units are not pipelined, and there's no forwarding. And basically, that's just another way of reiterating that we have one common data bus, hence common data bus. We have pipeline, and it's not common. It's uncommon, it would be UDB. And here's an important difference. Sub-I, subtraction, and branch, that should be branch not equal, sorry. Maintain consistency in the problem. Are integer instructions that each take 1 clock cycle to execute. So if I had an add D, meaning that would be a floating point addition, right? That would be different from, and give me an example here. So if I added add D, and then we had F6, F0, and F1, right? And then I had, and this was add I. Here's how that corresponds in the problem. The add D is a floating point, meaning it would use this floating point unit. And this add I is an integer instruction, which is using something different entirely. So before, we had a reduced MIPS single cycle data path that didn't do floating point because we limited everything to 32-bit instructions. Floating point performs What's the floating point IEEE thing? 754. So this is another good. Do you understand the difference between IEEE 754 and conventional 32-bit addition and multiplication? So Control Z, right? And so if in two instructions complete at the same time, one of them will have to wait. And so I'll give an example of, you typically want to give the tiebreaker to the instruction that was issued first. So here's how it works. First thing we do, if we recall from the TGO, we had 3 portions of the Tomasulo algorithm. We have an issue, we have an execution, and then writing the result. So to properly present the result, you have to show when the instruction is issued, when we execute, and when the result is written back to the appropriate value. So here we start out with load word. So if you recall, up here we said first load takes 8 clock cycles because if it's an L1 cache miss. So what we've represented here is you take the value, start with issue at cycle 1, it takes 8, right? And now we're at 9. And so what's going to happen is you take the next cycle to exit. You have 1 cycle to write the result. So oftentimes on exams, I'm going to see, this is how when I did this, I got tons of credit by doing this all over the place. +1, and this is, I can tell you that starts 2. I had to wait for here. Okay, so what's going to happen is you can actually kind of go through and see what's going on. Let me tell you what I mean. So you see here, multiplication takes 4 cycles, right? This one here. So let's go up to the instructions. So we don't need to go up to instructions. We have the result is loaded from the common data bus at cycle 10, right? And we have to wait on load word. And then it takes 4 cycles once that value is available to complete the execution of the instruction. So what's going to happen is we're going to issue it on the next cycle because the floating point reservation station is available to the multiplication. Right? Now it will not be available until this completes. And here's why that's important. Kind of give you a quick preview here. So you see how it writes at 15 and it's done at 15? This next multiplication, you see how it has to start at 15? The reason why is because we only have 1 multiplication unit. So here, we're able to start at 15. And that's actually 4 after this as well. Right? If we had a second multiplication unit, we might be able to improve performance. But here, let's just kind of stick with what we're doing here for now. So we have to wait. You have a comment section that will be available on the exam. So we have to wait on load 14. We have +1 here is 15, right? And then we see store F4, which we have updated in multiplication in store word. So here we're storing this back into R0, right? So let's see how long do store word instructions take. Store words take 3 cycles, right? So what that means is 15 plus 3 is 18. And then 1 more becomes 19. So here's where the benefit of Tomasulo's algorithm comes into play, these next 2. Right? So this column indicates iteration 1. The next column indicates iteration 2. So here we have R1, R1, 8. We issue it here. We have 4. And it take 1 cycle, as we state here in the problem. Sorry, let me go back up here. You see, sub I and branch not equal are integer instructions. that each take 1 clock cycle. So we go here, we see it's taking 1 clock cycle. It's also an integer instruction, so it stores the copy to the local copy of the register. Therefore, you do not need to use the common data bus. And that's why these two results are blank. So in order execution, in order issue, out of order execution. We have actually completed the subtraction and branch not equal at 5 and 6, even though we are updating the load word result at 10, we're updating our multiplication at 15, and we're updating our store word at 19. And so here's the other question I get. If I'm modifying R1 here, how can I guarantee that this value is being working properly? For those who want reviewing this on exam later. So here I've subtracted 8 from this copy of R1. So R1 is updated. But how can I guarantee this works? Well, the way the reservation station works is it passes the values along. It's actually, think about it this way. When you have the registers and you're writing code and you get the values out, those values, the value of R1 and 0 is being put into the reservation station to be added by an ALU. So the previous values, the correct values, have been issued into the reservation station. Therefore, when we update R1 here in the sub-I instruction, it doesn't affect the cache coherence. So if you think about it in parallel, and forgive me, it's a lot of people just nodding. I think you guys seem to understand, but we have a copy, it's passed along while the actual register is being updated. So that way when we do the next value over here, we don't need to worry about that one. So when we get to this next load word instruction, we're actually having the correct issue here, because what should happen is this R1 should be subtracted by 8 when we get this load. Yes?
So we'd have a problem, let's say, if we tried to sub I after 18, in other words, after 18 cycles.
What do you mean 18 cycles?
I mean, since we're completing that at 18, or it's not executing until 18.
This store word?
Yes.
No. The reason why is, you remember how store word takes a value from the, okay, let's go back to this is a good question though. This is why I brought it up, because this is the typical question that comes up. So think about in your data path when it's executing the address of store word, right? You're getting a value from the register, you're putting it to the arithmetic logic unit, you're adding the offset to calculate the address. When you put it in the reservation station, you're getting the initial copy of R1, right? So it's being issued at 3, right? If this subtraction was occurring before 3 for some reason, then this would actually affect what this value would be, and then it would affect cache consistency. What's happening is it's getting the value that we want out of the register. It's putting that value and 0 into the reservation station to be passed on to the arithmetic logic unit. And then that address that we're calculating is the correct address that's being passed to data memory. And then the correct value of F4 is then being passed as well. Did I answer your question? All right, good. Any other questions on the first iteration before we go to the second iteration? Okay, so here's where the one load buffer comes into play. So here I talk about we have one load buffer. So what this means is we have a second load word coming here, right? So normally we would be loading it to F0, right? Problem is we're still using F0. So that's what we're going to do is we're going to call F10. We're just going to add 10 to it and say, all right, I'm going to come up with just a new name for it. But really all I'm doing is loading a temporary copy and storing into F14 here. But you see how we've never changed F2, right? So here we've never changed F2, so we use the same value. Using register renaming, we're just subtracting 8. We're getting that value that we want. We're loading it to a different register. We're multiplying it by the same F2, and then we're going to store it in F14. And all we're going to do is store F14 back into the copy of R1 that we're going to, into the value, the pointer into the data memory that we want. But here's what we have to do before that. Notice how it's supposed to take 1, right? But it actually starts at 10. Why do you think it starts at 10? Other than the reason why I've written in the comment. It's a cache hit, which is supposed to take 1 cycle. Yes, Aaron?
Oh, I was going to say it had to wait for the first code word to
Bingo.
finish.
Exactly right. It has to wait 1. The +1 occurs here. That's why cache hit pointer to R1 updated by sub I instruction. And so that's the update. And so in the next version of the problem that I have down here, there's actually going to be 2 load and 2 store buffers. And you're going to see that this is actually going to become 6, 7, and 8. So by adding another load buffer, you're actually improving the performance, which then from 8 plus 4 becomes 12 and 13 and so on. 13 plus 3, 16, and 17. So in that case, you're going to actually complete the second loop before you complete the first loop. I saw a couple of people tilt their heads like a dog there. We'll go over it again. So here, then we add 1. We have 11 plus 4 because multiplication here takes 4 cycles. And we have 1 more. Store takes 3 cycles here. 16 plus 3 is 19. We do this again. Again, we do sub I, R1 and R1. We subtract 8. It's issued at 9. Goes to 10. Branch not equal goes to 10 and 11. Yeah. Oh, does anybody have any questions? All right, so this diagram here, I think you guys picked up on this really quickly about me adding and subtracting in different loops, specifically in the integer instruction, right? So basically, this is just addressing the same question that you asked about how it maintains the proper value, because it's actually been subtracted by 8, but here it's been actually loaded into a different reservation register in order to be able to do it. So here, 8.4, it's the same problem, except the only difference is I have 2 load and 2 store buffers. So how does this affect our execution? So let's go to the result again. Here it's the same thing. 1, we issue it. It has a 8 clock cycle delay because the first load is a miss. So it goes to 9. We go to 10. Multiplication, it takes 4 cycles after we write the result, plus 14. We then take another cycle on the common data bus for 15. We take 3 plus, we have 15 plus 3 because it takes 3 cycles to do a store. So we get to 18 and 19. So we issue those 3 each cycle. Sub I, we issue it 4. Branch not equal, we issue it 5. They each take 1. They're integer instructions, so therefore they do not require the common data bus. So this is where it gets different. We load everything here, but we now have this. Six, 7, and 8. And then plus 4, 8 becomes 12. Right? Take another cycle to add there. We have 3 for store word. That becomes 16. And 17. So what ends up happening is because we're able to take advantage of the loading and it has to wait, but this one doesn't have to wait because once it's already got it, we can just go. We are actually completing the second cycle before we complete the first cycle.
in order to issue, out of order execution. Okay, so does anybody have any questions about this? I know we got like 8 minutes left in lecture, and usually people have lots of questions about Tomasulo. No?
On the exam?
Yeah. You'll have the columns.
Okay. And we fill in the instruction part too, or?
Yeah. So here, the one thing, because it's going to be 2 iterations, because asking more than 2 iterations, just you're not going to have the time for that on an exam. You're going to have, they're basically going to be the same, except in the second loop, the only difference is you want to take advantage of this register renaming here. It's going to be very similar. It's going to be a very similar problem. Okay, well, in that case, let's kind of go over this concept of branch prediction. So branch prediction, the TGO should only be that. Branch prediction, a digital. So basically, the whole idea is what happens when we have massively parallel processing, and then we have an issue where we have to guess. We encounter a branch in one of the parallel branches, but we're calculating one of the 2 values we're comparing in another processor, and we need to get that in there. So branch prediction plays a critical role. You know what? Let's cut off at 8.11 from Tomasulo, because I think branch prediction is something you just want to go over all together. And we'll do that, and then we'll do exam review, questions about the project, and then I can send you guys off on your Thanksgiving break. So I will upload this, but it's going to be the problems that we did up through and the TGOs up through 8.11. So does anybody before I dismiss you, does anybody have any other Tomasulo related questions? I'm sure when you work through it, you'll have some more.